Hello, my name is Jose Benavides, and we're going to be finding formulas using integration by parts. Now, how do we find formulas using integration by parts? This is a step-by-step guide that will help students. This step-by-step guide will help students currently taking Calculus 2, as well as engineers or students that have taken Calculus 2. Using integration by parts and learning to master it will simplify the process and save time. This task can take from 5 to 20 minutes depending on the functions used in the integral. By the end of the section, students should understand how to integrate by parts. Now, the time that it'll take for us to complete this will be about 5 minutes. Typically, that's around the same time that we'll use for anything when we're starting. But as we continue and we learn to master the process can take about 1 minute, if not less. Okay, so do not continue unless you have taken Calculus 1. This is the reason we need this is because we need a fundamental basics about Calculus 1. It's a lot harder to understand if you've only taken pre-calculus or college algebra because we're going to be using terms like integration, derivatives, logarithms. These are functions that some of these functions we see in pre-cal, but for the most part, a lot of it is in Calculus 1. So you are recommended and it is needed to take Calculus 1 in order to understand this process. If you understand some of the terminology, that's great. If not, I really do recommend you take Calculus 1 before you continue. And you don't really need Calculus 2, but this is to help somebody who is taking Calculus 2. That could be you or a friend or anyone that's watching. Materials needed. A sheet of paper with the integration formulas. So now, you can find those online. I will provide this at the end. A sheet with integration by parts formula. That one I should have it with that same integration formula. It'll just be separately. And we will have paper and pencil. Steps to complete integration by parts. So the first part we need is our formula. So our original function is the integral of u times dv, which we can see here where it says number 1, u dv. What we will have as an end result is what we see uv minus the integral. This is the integral of v du. Now, this is not a very complicated process, but what makes it complicated is what we use inside of the integral. You'll see that later on as you have more examples, but right now we're going to use something simple so we can understand it. So now we're going to pick our u function. The way we pick our u function, as you saw in the previous slide, we had a u function and a v and a du and a dv. The way we use our u function is, or how do we pick it, is we use liat. So we find the logarithm, the inverse function, an algebraic function, the trigonometric function, or an exponential function. Whichever one comes first is our u. So for our example, we have a logarithm and an algebraic function. So like I said, we go with the one that comes first. So we see that we're going to choose the logarithmic function first because if you look at liat, the logarithm comes before the algebraic. So our u is going to be ln of x. Now, once we have our ln of x, let's write that u equals ln of x. Now, the next step is we need to find our dv. Now, that's simple. We already found our u. The rest that we didn't use is our dv. So for example, we used ln of x, we were left with x and dx. So now that's going to be our dv. Our dv will be x dx. You'll see why we need the dx here in the dv later on. But that's kind of the key is once you pick your u function, the rest of it becomes your dv. So always remember that. For the next step, we take the derivative of the u function. Now, this can vary to whatever it may be. This can be a simple x function, or how we see here an ln of x, or this can be a sine of x, cosine of x, whatever it may be. But for ours, we're seeing that it is ln of x. So we go for the formula sheet. We're going to see an example that I wrote here. D over dx, ln of x is equal to 1 over x. That's just a formula that we have. That's much as I can explain for that. So we take the derivative of u. When we take the derivative of u, we have to write du because that's explaining our derivative. Now, once we take a derivative of ln of x, we should have 1 over x times the derivative of x, so dx. Always remember that. When you take this derivative, always have the derivative of x next to it, whether it be, this doesn't matter for what function you may have. You may have a y, a z, an a, a b, whatever it may be. But as long as it has the derivative, right? This for my ln of x is 1 over x times the derivative of x. Now, we need to integrate dv. So when we integrate dv, see how here my u became du? So the integration is going to be the opposite. From du, it's going to go to v. And we do that for our x dx. So now here, you can see that in your formula sheet, you should have something as the integral of x dx is equal to x squared over 2. Or I should say x to the n is equal to n plus 1 over n plus 1. So the reason for that is because all they're saying is whatever your n function is, or your n number, for example. So here, my n number would be 1, because x to the 1 is just x. And then we would add a 1 to that top one, which is why we have x to the 2, over 1 plus 1. So whatever we have up here, we do to the bottom. So if this had a 2, for example here, it'd be 2 plus 1, which would be 3 here, over 2 plus 1, so it would be 3 down here as well. And we found our v. We have that v is equal to x squared over 2. The last step on this slide is we need to substitute our u, v, and our du functions, because if we looked at the functions that we had at the beginning, we had u times v minus the integral of v du. So those are the 3 functions that we have and we need. So now we can substitute. We can substitute the u that we have here as ln of x here, ln of x times v, which is x squared over 2, minus the integral of x squared over 2 times 1 over x dx. Now, we need to simplify our integral, the part that's on the right side. Let's simplify it from what we see. So we look at our function here. We have x squared over 2 times 1 over x dx. So now if we remember, we go back to college algebra, we know that if we have 2 functions, so we have like 2 variables that are one over the other, we would subtract the exponents. So here we have x squared over x. So then we would subtract 2 minus 1, because we know that these 2 will cancel, like this bottom one will cancel 1 from the top. If we had, let's just say that instead of it 1 over x, it'd just be x. So then the exponents would add, right? Because they're multiplying, they're not dividing. So they're multiplying, they would add the exponents. If they're dividing, you would subtract the exponents. So that's why we're left with the integral of x over 2 dx. Now, we need to integrate that function. Once we integrate that function, we'll see the later steps. So the same way we did earlier with that dx, we're going to do with this one. The integral of x over 2 dx, we need to add 1 to the top, to the exponent. So we add 1 plus 1 over, now we have a 2. If you have a 2 or a number, typically that number will multiply whatever you did to this top. So if I had, instead of 2 plus 1, the bottom would be 2 times parentheses 2 plus 1. And then, so for here, we have 1 plus 1, that's 2, times 2 gives us 4. And at the top we have x squared. So now we rewrite the new function as ln of x times x squared over 2 minus x squared over 4. So now, we need to check. We should see this from the very get-go, from the very beginning, that, okay, do we have limits? Okay, let's just say we did. Let's just say we have limits from 0 to 1. So now we would put that function into brackets, and we would write on the right side 0 to 1. That indicates that this function, we're going to, at the end when we integrate it, we're going to substitute those numbers into this integral. So now, when we do this, we're going to substitute one function with the number 1 and another function with 0. So if we look here on where I have the number 2 at a, I substituted all the x's on the left side with a 1 and all the x's on the right with a 0, just the way I explained earlier. So now if I look here at the picture, I know that the right side was all 0, right? Because if I look here, the ln of 0, we don't know what that is, times 0 just becomes a 0. And then a 0 over 4 is also 0. So you don't worry about this number anymore. So now we look at the left side. We know for a fact that ln of 1 is 0. So that for sure just cancels out. But we have a minus 1 squared over 4. Now, the 1 squared over 4, we don't do anything else to it, right? Because there's nothing else that we can do to it. We don't multiply it times another number or whatever it may be. We just simplify the 1. 1 squared only gives us 1. So then now we're left with negative 1 over 4. That is our answer. We had a limit. Now, if we didn't have a limit, just like integrating in calculus 1, if you integrate a function without limits, you always add a constant. You always do plus c. Why? Because we don't know what that constant is or what that number may be. Because they're like, if you were to take this integral, you would get back the function we had originally, but we know that a constant, if you take a derivative of a constant, it just becomes 0. So that's why we always have that constant, because we don't know if we have it or not. And yeah, for 10b, we have ln of x times x squared over 2 minus x squared over 4 plus c. So in conclusion, like I said earlier, this process is easier to understand if you have taken Calculus 1 or a calculus course in high school. This process does help simplify integrating. However, it is a little bit more challenging. Once you master the process, you can skip steps. So I could have skipped the several steps, but just to explain why I did what I did is why I kept most of the steps. You could have skipped, like, for example, the zeros, because I know that, like, when we were taking the limits, I could have skipped the whole 0 part because I know that all those numbers, because they had an x, they were going to become 0. So I wasn't going to use that anymore. The 1, for example, I could have skipped some steps too. Earlier when I did the dx, du, all that stuff, a lot of that you can skip, but for now, keep it simple. Thank you so much, and goodbye.